last time we defined it, we talked about some examples. Let's remind what the definition is briefly. So we are looking at permutations of permutations of this is from last time is a permutation. So I1, I2, I sub n of numbers 1 through n, such that none of the letters, none of the numbers are in their original positions. So such that none of the i's are integers. Is in its own position. Okay, so original position meaning 1 through this kind of situation. Okay, so we are then I want to be nothing on I2 to be nothing to 2 and I sub n nothing to n. This is the kind of permutations we are interested in. Again, this is just an abstraction of different kind of situations you may think of. We started with the head check problem, namely that people check their heads in a restaurant, let's say, and the waiter is returning them, and in how many ways the heads can be returned so that nobody receives his or her own head. This is the kind of situation I'm thinking about here. So here is the theorem that counts it. So we had a notation for them, and this is, we introduced Dn, and this is the number of one of n. And the theorem we wrote but did not prove last time is that for n greater or equal to 1, this number is n factorial times the alternating sum of 1 over k factorial, so I'll just write it this way. K0 to n. This is an alternating sum minus 1 to the power of k over k factorial. Okay, so let's prove this. So the proof uses inclusion exclusion principle. Okay. So namely, here's what you do. We set S to be the set of all permutations, just as usual. All permutations of 1 to n. And then A sub I to be the permutations which leave I in its place, namely the number I from this list is in the ith position. So permutations in S such that I is in the ith position. For instance, A1 is all the permutations, corresponds to the set of all the permutations which leave 1 fixed in its first place. Okay, so what we want is, obviously, exactly the complementary of all of these things. So we are interested in A1 complement, A2 complement, and A2n complement, and the size of this set, the cardinality of this set. And that, as we know, inclusion exclusion is the tool to count these things. And one thing to observe again is that the situation is symmetric with respect to the numbers. So is symmetric. In other words, A1 and A5 are the same, basically, in that sense. So with respect to I, and so we have I'll write the formula that the inclusion exclusion principle tells me. So k equals 0 to n. It's an alternating sum. And then I'm going to have n choose k here. Remember how the formula works. At each step we are looking at k-tuple intersections. And if the size of these sets are the same, it's about how many k-subsets you can have, and I need to have the size of these intersections here. So I'll write just as before alpha sub k, where alpha sub k is equal to the size of the cardinality of a k-tuple intersection. Of A sub I. Okay, where alpha sub 0 corresponds to the entire set. So let's find out what these are. So, as I just said, alpha sub 0 is everything. So this is n factorial, the set of all permutations. I'm going to need alpha sub all of them. So what's alpha sub 1? These correspond to alpha sub 1 corresponds to the size of each A sub i's. So can you tell me how many permutations of n numbers, 1 through n, leaves I permutation in its place, I number in its place, n minus 1 factorial. So one of the numbers is fixed, the rest is around So likewise, what about alpha sub 2? So here we are going to be interested in measuring these intersections. Now let's go back to A sub I. What this corresponds to is permutations which leave I in its fixed place and J in its fixed place. So as a result, this number is at minus 2 factorial. So the pattern is clear, I suppose. So I'm going to have as alpha sub k, I'm going to have a k-tuple intersection, so it can look like something like that. I sub 1, I sub k, for instance. So this is just n minus k factorial. So this is n minus k factorial for all k from 0 to n. Okay, this is what I need in the sum. So, dn. Inclusion exclusion gave me the formula. And the formula is this. I'm just copying it. With the alpha sub k, and now I know how to calculate the alpha sub k's. Now remembering that n choose k is n factorial divided by k factorial n minus k factorial. there a question? So I have n factorial part has nothing to do with k, so it can be factored out. What we will have here is in the denominator k factorial as a result. The cancellation, which is what we want to do. Are there any questions about the proof?
Is there this point where the n factorial counts like what pulls out of? Is that using the zero term?
No, just look at this. So I have this term here, right? Nk n minus k factorial, which is equal to, say, just remember the formula for n to k. Now, this factors out because it's independent of k. This is what I here, so this will survive along with the sign minus 1 for k. Any other questions? Now, once more, just like I told you last time, all of this assumes the symmetry with respect to all numbers here in general, whatever objects you are dealing with. So I can use this special formula for inclusion exclusion. For instance, in the case of letters, remember we worked out the arrangements of 5 letters. That was the one example I did. So letters of the word, 5-letter word. Gecko, I think we did. So I asked you how many permutations are there so that the string is different from the word gecko. Completely disagrees in that sense. So no letter is fixed. So this was just basically d sub 5, and we calculated it to find and found that it's 44. It was important, and it is important that no letter is repeated. Okay? So let's just write this as a remark in this. I mean that when there are repeating letters, of course you can again talk about the arrangements, but it just is a different problem. This formula cannot be applied there. So this is something to be careful of. So again, from last time, I'll just write the answer from last time. All letters. Remember the number of permutations that completely disagree with the word gecko. It's simply just arrangements of these 5 letters, and we found that this is 44 from last time. And now I wanted to say this remark that important that no letters are repeated. Okay. Now, for instance, if I ask you how many derangements of the word mom, how many derangements of the word mom? None, right? So normally we know the derangements of 3, so which would be correspond to B3 is 2. We wrote them down last time. But in this case there are none, so there are no derangements of mom, even though B3 is 2. So it's just totally different things. Okay, so probability, let's touch upon the probability. That was like the original, this is how we started with the type check problem. So event that no integer from this list, from this list of integers is fixed, okay, in its own fixed meaning, in its natural position. Sometimes one talk about fixed points of a permutation of an action, things like that, which really means that, say, number 1 is fixed in position 1, this means number 1 is a fixed point of that permutation. So in that sense, we are interested in things where you don't have any fixed points, or any fixed numbers, any fixed heads, this kind of thing. So anyway, let's, if E denotes the event that no integer is fixed, so we can talk about, so let's just write, so this is exactly the kind of thing we are interested in here, so this is the arrangement, in other words, size of this set, which, as we have just figured out, by the theorem is this. Now, one can talk about probability of this event happening. So this is, of course, the size of E divided by the size of all permutations, which is n factorial, which is dn over n factorial. Okay. And then, of course, we can write k0, 1 minus 1 to the power k over k factorial. Right? Okay. So now let's just look at the series expansion a bit further. So here I need to just remind you a simple fact from calculus. What's the expansion of e to the x? Taylor series expansion I'm talking about. Anyone? Yeah?
X to the k over k factorial.
X to the k over k factorial. Perfect. Okay. Now, again, you may remember that this is a very nice Taylor expansion. It converges everywhere. The infinity radius of convergence. So, in other words, these two things are actually really the same things. Now, as a result, I can write what e to the minus 1 is. And e to the minus 1 is just the sum that we are interested actually in. So, this is the Taylor series expansion. Converges everywhere. Okay, so now these two things look very similar, except one is an infinite series, one is a finite sum we have. We can look at the difference. So e to the minus 1 minus dn over n factorial, which is the probability that we are interested in. So this is just sum from k starting from n plus 1, right? All the way up to infinity. So I got rid of this finite piece out of it. So of minus 1 to the power k over k